House Reporter is a good newspaper. It's put out by a good staff. The faculty advisor happens to be me. But I don't really do much advising because most problems are handled in staff meetings. Take the matter of our deficit. Soon after the school term started, we could see that our costs were running higher than our income by about $5.50 a week. Skippy, the business manager, recommended that we make up the deficit by raising the price of the paper from 4 cents to 5. The majority voted against him, but it was still up to Skippy as business manager to find the answer. The only person who agreed with him was Bill, the circulation manager.
Well, now what? You certainly didn't convince Jack and the others about raising the price of the paper.
Nope. You know, Bill, we just got to make them see that raising our price is the only way we can make up our deficit. I thought when I showed him this article about the rising cost of newsprint that...
Say, what is it?
It was only a simple bar graph, but it showed a number of facts in a vivid manner, and it gave Skippy an idea. They could make a graph that would show the facts about the cost of putting out the paper. Both boys had made some graphs in their mathematics classes. Now, here was a chance to put some knowledge to work. A graph is a visual device for showing the relationships existing in data. These relationships are usually graphed on squared paper. Skippy drew a horizontal line and wrote down first year and each succeeding year in which the paper was published. These were spaced at equal intervals. Then on the vertical scale at the left, he let each interval represent $10. Bill checked his figures and found that they needed to go only as high as $100. The first bar was drawn to a height of 66 on the vertical scale. This bar represents the sum of $66, the average weekly cost of putting out the paper the first year. Now, for each succeeding year, another bar was drawn until the average weekly production cost for each year had been graphed. The bars are all the same width. The only variation is in height. The boys were satisfied that they had translated their information accurately into a vivid picture, one that the staff would really understand. When I dropped in to see why they were working so late, they were eager to show me what they had done. I agreed that they had made an excellent bar graph.
I just thought of something, Skippy. This shows why we need more income to cover the rise in the cost of putting out the paper. But that's only part of the problem. Jack and the others are afraid that if we do raise the price, our circulation will drop, and we'll have less income than we do now.
Bill had raised a good point, so I reminded them that there are other kinds of graphs. If the bar graph didn't tell the whole story, perhaps a line graph would help. They got the idea at once. When I left, they began a search. Because graphs are a kind of writing, newspapers and magazines use them continually to present information to readers. So it wasn't long before Bill had found in a reliable magazine a good example of a line graph. This particular graph, by using 3 lines, shows a comparison of changes in 3 items over the same period of time. It was this graph that gave the boys the idea for comparing the circulation of our paper with that of the other local high schools. It took them several days to gather circulation figures from the other schools. Then one evening, as I was leaving school, they showed me what they had done. It was a line graph. The boys told me how they had made it. To make less plotting, they took the average weekly sale for each month. They started with their squared paper, or grid, and drew 2 perpendicular axes. Along the horizontal axis, which is called the x-axis, they arranged the 10 months of the school year. Along the vertical axis, which is called the y-axis, their scale of values was to represent circulation figures. To avoid distortion, they began at 0 and dotted in 1 square to show that they were cutting out from 0 to 800. Beginning at 800, they let each interval represent 100 papers. Since the largest circulation figure was 1760, they numbered only up to 1800. Captions were added for each scale of values to tell what relationships were being shown. The boys explained to me how they plotted the average weekly circulation figures for our school. For September, they found the average to be 1,550, rounded off to the nearest 10. On the vertical line for September, they followed up to a point midway between the 1500 line and the 1600 line, or 1550, and located a point. Our average weekly circulation for October was 1500. This was plotted the same way, by finding along the horizontal axis the line for October, and along the vertical axis the line representing 1500. Where these two lines meet or intersect is the plotted point that represents a weekly average of 1,500 papers sold in October. The circulation figure for each month was plotted in the same way. This is the line that represents our circulation for last year. To represent the circulation of the other schools, the boys used different lines. This key or legend explains the lines. They let this line represent the Lincoln School. Notice the terrific drop in November. This was the month that Lincoln School increased the price of its paper. Lee High School also increased the price of its paper. This was done in January. See the reaction on the graph? Circulation fell in January. In the same month, Jefferson School raised its price. Again, circulation fell. But the striking thing, the thing the graph showed us at once, was that in each case, circulation steadily recovered. This was the vivid picture the boys showed to me, and the next day to their editor.
Maybe so. I still think we can put out our paper without raising the price. Besides our sales, what about our income from advertising and from the activity fund and from alumni subscription? Now, I have an answer to that right here. Oh, no. Oh, sorry, I have to leave it. Well, I'll see you at the staff meeting tomorrow.
Yes, Skippy had an answer, and a very clear one. It was a circle graph that he and Bill had made. In a circle graph, the whole circle represents the amount of money needed to put out the paper each week, an average of $91. Each sector represents a source of money used to meet production costs. From sales came their biggest amount, 66%, which was about $60. 20% of the cost was met from the advertising in the paper. The activity fund of the school supplied 5% of the money, and 3% came from alumni subscriptions. But notice that all this money did not quite make the whole circle. The graph clearly showed our deficit of 6%, or about $5.50 per week.
And then I'll say, this is the deficit we have to meet. We can't get any more money from the activity fund. We've got all the advertising we have space for. Our alumni subscriptions won't change for a year. And we know we can't sell more than the usual number of papers. So the only solution is to change the sales price from 4 cents to 5.
Then they'll want to know where we'll stand if circulation falls off.
And we'll answer that by showing them this.
This was an equation graph, sometimes called a formula graph. It showed the relationship between the income from sales and the number of papers sold. To make this graph, the boys started with the equation, income is equal to 5 cents times the number of papers, or simply, I equals 5/100 N. This equation or formula graph shows how income depends upon the number of copies, and this relationship the boys graphed. On the basic grid, they let the vertical scale represent income, or I, and the horizontal scale represent the number of papers, or N. Then they use the equation to plot several points by assigning certain values to N and computing the corresponding values for I. For instance, if 200 papers were sold, that is, if N equals 200, then I equals 5 cents multiplied by 200, or $10. And on the graph, this point, 200 papers and $10, would be right here. To plot another point, they let N equal 1,000. Then, according to the equation, I became 50. The intersection of these two lines on the graph, 1,000 papers and $50, was here. Now a line connecting these points gave them any number of answers to their equation, because any point on this line represents a set of values that will fit the equation. Notice that the line goes through the point 0, 0, called the origin. If 0 papers were sold, the income would be 0. To see how much the income would be for 1,500 papers, they simply found the value for 1,500 on the horizontal scale, moved up until they reached the graph line, and then moved across to the vertical scale to get the answer, $75. Then they decided to go one step farther and graph the equation using the old price of 4 cents. By substituting values for n and I, and following the same method of plotting the points, they got this line for I equals 400th n. Now they could easily compare the income from a 4-cent paper and a 5-cent paper for any circulation figure.
When we sell 1,500 papers at 4 cents, we make $60. But we need $66 to cover our deficit. Now, if we sold the paper for 5 cents, we could make $66 by selling 1,320 papers. Why, that's less than our average circulation, and we could still make up the deficit. Then, too, to make $66 at 4 cents, you can see from the graph that it would nearly take 1,700 papers. But we couldn't sell that many, so we'll just have to raise our price.
But what if our circulation drops way below average? Say to 1,000.
Well, then I think the answer is right here. Our line graph shows that the circulation did drop when these schools increased the price of their papers. But it also shows that within a few months it climbed right back again.
The boys had done a good job of presenting their case, and they had learned a good bit about graphs. First, there was the bar graph. This type shows relationships very clearly. Separate items, for instance, such as the exports or imports of a nation for a number of years, can quickly be pictured on a bar graph. Information of a continuing nature, such as stock market variations, is often set down in a line graph. One of the favorite methods of telling the taxpayer how his money is spent is to show it in a circle graph. The graph of an equation reveals relationships of a numerical nature. This one, for example, shows the relationship between certain characteristics of a photographic film. And graphs are equally vivid no matter where in the world they're made. This bar graph shows coffee exports from Brazil to the United States over a period of 40 years. This line graph, with captions in several different languages, compares the annual tonnage of ships entering the port of Ghent, Belgium for 35 years. A circle graph is equally effective in showing where the taxpayer's money goes in any country. And here the various kinds of graphs are used together to present a mass of information about the pre-war population of Japan. Around the world, graphs are an important kind of communication, and they help Skippy and Bill to communicate their idea about the paper, because the staff voted unanimously to increase the price.
Say, I've got an idea. Why don't we publish these graphs in the first issue of the 5-cent paper? Then we can show the whole student body what the facts are. They'll understand why we had to raise the price.
Say, that's a good idea. Then maybe our sales won't drop off as much as they did in the Lincoln School.
Oh, sure.
And that's how the staff of the Ross Reporter solved the problem of the deficit, by learning how to use a powerful language, the language of graphs.
It's easy enough to see that the kinetic energy of the car near the bottom of its motion is being converted on the way up into potential energy, and is all potential energy at the top of the path. The potential energy now converts back into kinetic energy, and at the bottom there it's all energy of motion. The same kind of thing is happening here. Watch it in slow motion. Kinetic energy, the energy of motion, now becomes the energy of separation between the ball and the earth. And down at the bottom, it all goes into potential energy of compression. Now, all along, all the time, the ball is losing energy. What about the principle of conservation of energy? You know it loses some by friction with the air, but it also loses some when it hits the glass plate. It's a lot easier to photograph the compression of a rubber ball than a ball bearing, but the idea is the same. As you can see, the energy loss at impact is important, but it's easier to discuss the energy loss due to friction with the air, and once you've understood that, you'll understand the effect at the solid surface, too. Let's go take a look at a model of a gas we've got over here. First, I'll drop in one molecule, and now I'll add another, and now another. And even with only 3, you see how ridiculous it would be to try to keep all these motions in mind. Even in slow motion, even though it's easier to see, you'd still have to be outrageously patient to keep track of all of these motions. But with enough molecules, this motion, this chaotic motion, takes on a certain kind of order. We'll use this barrier for a piston. The effect of the impacts of many molecules tends to average out, and we see a smoothing effect. Now, in a real gas, we substitute average quantities. For instance, for the bouncing of the molecules against the wall, for the collisions that impact against the wall, we take an average quantity called the pressure, the force per unit of area. You'll read it on a pressure gauge like this. And for the motions of the molecules inside the gas, what we do is to substitute for their average kinetic energy of motion, average kinetic energy of linear motion, a simple quantity called the temperature. You know, what you read on a thermometer. Now, what gives us the privilege of substituting a concept like temperature for the average kinetic energy of motion of the molecules? Temperature you've grown up with all your life, and the kinetic energy of a molecule is something that maybe you just hear about. The argument is really simple. It goes something like this. The kinetic theory of gases, the theory, says that the pressure in a gas is proportional to the average kinetic energy of the molecules. The average kinetic energy of the linear motion of the molecules. The text has it all worked out, but let's write it this way. One of these quantities, mv, comes from the momentum change at impact. The molecule hits and it bounces back, and the momentum change is, of course, proportional to the momentum of the molecule. And the other v comes in because the faster the molecules are going, the more molecules hit the wall. That's easy enough, and that's why we get the mv squared. Now, experiments say that the pressure in a gas is proportional to the absolute temperature. The pressure is proportional to the absolute temperature. This is a little more complicated than I make out here, simply because we use this relation to define absolute temperature. In order to clarify this notion, let's go do some experiments over here. We're going to observe the pressure of a gas as a function of the temperature. Here we have a container with 2 atmospheres of helium gas. Andy, would you take this? We're going to immerse it first in boiling water, then in melting ice, then in dry ice and alcohol, and finally in a bath of liquid nitrogen. Okay, Andy, can we start taking some readings? .49.
1.81. 1.38. 0.55.
Now let's take a look at the pressure readings. They go all the way from above 2 atmospheres, from 2.5 atmospheres, all the way down to half an atmosphere at the temperature of liquid nitrogen. So let's try the experiment again with another gas. This time we'll pick oxygen. Okay, Andy, let's go.
2.43. 1.81. 1.39. 0.31.
Let's take a look at the oxygen data. Compare the two sets of readings. Remember, we forced them to fit at room temperature at 2 atmospheres for both. But at boiling water temperature and at melting ice and at the dry ice temperature, they agree perfectly, as well as we could read them. But down here at the temperature of liquid nitrogen, the oxygen reading is very different from the helium reading. Some of you may have guessed already what went wrong there. Let's take a look here. Here's some liquid nitrogen in a tin can. And let me hold this so you can see. You can see the oxygen from the air condensing on the outside. And if you don't believe that's oxygen, just watch what happens. So you see what happened in the experiment is that the oxygen partly liquefied in the bulb. If we had taken a lot less gas, for instance, if we had put in less than 1/10 of an atmosphere in both bulbs, then the readings would have agreed all the way down, right down through the nitrogen point. What I'm trying to say is this, that for gases that are thin or tenuous, like the gases in the upper atmosphere, if the pressures agree at one temperature, if you take a certain amount of gas so that they agree at one temperature, they will agree all the way up and down. So we take this universal property of gases as a way of defining the temperature scale. In order to clarify that, let's go look at the graph right here. Let's plot the pressure against temperature, but we've got to pick a temperature scale. Let's set the temperature of melting ice at 273 degrees arbitrarily, and we put our point there. Now what we do is to draw a straight line right through that point and the origin. Then we can put our other data on that graph and say, by definition, that the pressure is proportional to the temperature. And that defines our temperature scale. Now, if we want to read the temperature of boiling water, say, we put its pressure at 248 right there and read its temperature. It comes out, of course, 373 degrees. That gives us 100 degrees between the temperature of melting ice and the temperature of boiling water. And that's exactly why we chose the 273 for the ice point. So we'd get that 100 degrees difference between those two temperatures. Now, if we want to find the temperature of the carbon dioxide slush, we plot its pressure at 1.4 right there. So it comes out 220 degrees absolute, and the liquid nitrogen temperature, the pressure from the helium graph, of course, we put right at 0.55 there. So it is at a temperature of about 80 degrees absolute. Now let's plot the oxygen point here. That 0.29 falls off the graph. You knew it would. And you know why? We started with too much gas in both of the bulbs. Too much helium, too much oxygen. They weren't tenuous enough for them to agree all the way up and down. Let's go back to the logic. What we said was simply this. From the theory, from the kinetic theory of gases, the pressure is proportional to the average kinetic energy of linear motion of the molecules. And we've just discussed that the pressure in a gas is proportional to the absolute temperature. We simply identify one with the other and say that T, the temperature, is proportional to the average kinetic energy of motion of the molecules. We simply measure the average kinetic energy of translation of the molecules by observing the absolute temperature. When a gas is hot, the molecules are moving fast. When it's cold, the molecules are moving slowly. But all of that energy is chaotic. It's random. Now, in a mixture of gases, with heavy molecules and light molecules, the heavy ones are moving relatively slowly, and the light ones are moving fast to keep their kinetic energy up. Even in the extreme case of these particles of smoke, in this Brownian motion experiment, the average kinetic energy of the smoke particles is the same as the average kinetic energy of the molecules of the air, even though these smoke particles contain millions of atoms. Okay, let's get back to our original question. What happened to the bouncing ball when it lost energy to the gas? In order to show what we think happened, we'll have a model. Here's a frictionless disk, which we'll let slide down an incline, gaining kinetic energy as it goes until it hits. Now, what would happen to that if it went through some gas? The best way to show that is to bring on some gas. And the disk comes to a Brownian motion halt. Let's try it again. The orderly kinetic energy of the disk is transferred into disorderly random motion of what we have called the molecules that were hitting it. It may not be perfectly apparent, but every time a molecule hit that disk, some of the energy of the disk was transferred over to it. In that way, the disk lost its energy to that gas of molecules. In exactly the same way, when this falling ball that we were talking about falls through the air, its energy is transferred into the random energy of motion of the gas, random energy of motion of the air. And when that ball hit the table, hit the plate, then the same sort of thing happened. The orderly energy that you could see, both potential energy and kinetic energy, were converted over into energy of motion of the molecules, of the plate, and of the ball, and of some of the air. So we have to ask the question, is the energy conserved? It certainly is. Then where does it go? At least you know what it doesn't do. It doesn't just go backwards like this. What usually happens is that we get what we call thermal conduction, heat flow. Energy flows from a hot body to a cold one. Let's go take a look at a model of that over here. Here is our old friend, the marble machine. Let me turn it on first. The marbles in the lower compartment have no effect on the ones in the upper compartment. They are separated by two bars with an insulating airspace between them. Now suppose we take away that insulating barrier. It's a little clumsy, but let me try it. Right, just like that. With the insulating barrier removed, the marbles in the lower compartment are now able to transfer their random thermal energy to the marbles in the upper compartment. And that's exactly what happens when we heat something with a flame. Here's a flame, here's something, bulb of gas, and the molecules in the flame that are moving very rapidly transfer their kinetic energy first to the bulb, and then to the gas. Now, some of the energy of the flame goes into the energy of the gas, and the temperature goes up, and the pressure goes up. Now, what do we mean by the principle of conservation of energy? Energy appears in various forms as kinetic energy and potential energy, and sometimes it's orderly, and sometimes it's random. And when it's random enough, we call it thermal energy. Some people call it heat. What we mean by the principle of conservation of energy, then, is simply this. We believe that energy is never created, never destroyed. We may convert it from one form to another, from orderly motion to random motion. We may fritter it away by warming up the air, by warming up the ocean. But it's still somewhere. Now, there's one more thing we've got to discuss before we finish. Now, when we transport energy, we might transport the whole material body, complete with the energy and all, like throwing hot rivets or carrying coal. Or we might have energy transported by molecular bombardment. We've just been discussing that. We call it heat conduction. Or energy might be transported by radiation. Usually this takes the form of electromagnetic radiation, say infrared light or visible light. In fact, most of our energy comes to us that way. It comes to us from a star, our own personal star called the sun. In the sun, the energy is stored by the atomic nuclei. And this energy is converted into random thermal energy in the sun, and that random thermal energy into radiation. And the radiation comes through space, and some of it is captured here on the Earth. And some of that, by the process of photosynthesis, is converted into trees. And the trees were converted into coal or oil. And some of that fuel was converted into hot steam, or something that turns a turbine, or runs a motor. And we get orderly mechanical energy out of that. But regarding the conversion of thermal energy into mechanical energy, and then mechanical energy back into thermal, more of that in the next film.
examples of the transfer of energy from one body to another and from one place to another. We want to look closely at some changes like these and see just what is happening to the energy at each step. Over here, we have a kind of gibbet, and hanging at the top is a heavy iron ball. The ball, which has a mass of 10 kilograms, has been raised a distance of 3 meters. Now, in this condition, the earth and the ball are attracting each other. And if we release the ball, then the gravitational force downward on the ball, upward on the earth, will accelerate the two masses toward each other, and they will gain kinetic energy. Not very much of the energy will be gained by the earth because, of course, it has such a great mass. So we'll focus our attention on the ball. Watch. The downward force on the ball accelerated it. The ball gained kinetic energy all the way down. This energy was transferred from the system of two attracting masses to the moving ball. Now, when energy is transferred, this means that work is done. Work transfers energy, and the amount of work gives us the amount of energy transferred. Let's investigate this work. The downward force on this ball, acting through a vertical distance of 3 meters, did a definite amount of work. We can measure the force. "98 newtons here. 98 here. And 98 again. Of course it doesn't change. We're changing the distance so little compared to the total distance between the centers of the earth and ball that we couldn't expect to find a change in the force. Now we can calculate the work. All we have to do is to find the area underneath this curve of force versus distance. This is a rectangle since the force is constant. So we have F times S for the area. This is equal to 98 newtons times 3 meters, or 294 joules. This is the work and should give us a measure of the energy transferred to the ball. The kinetic energy of the ball is 1/2 mv squared, and we know m, it's 10 kilograms. And now we must measure the velocity. We're going to measure the final velocity of the ball by timing the last 15 centimeters of drop. This is the device that we'll use for this. This frame has 2 wires 15 centimeters apart. We're going to let the ball drop through this frame, first breaking one wire and then the other. The wires act as switches. The first turns on a timing device, the second turns it off, and the time elapsed will be read on this meter. I'm going to do this for you with my pencil just to show you how it works. Watch the meter. That took about 18 milliseconds, or 18 thousandths of a second. Now I'll have to reset this again because this is what we're going to put in the path of the ball, and while I'm doing it, we'll get a frame put over the sandbox to hold this timer firmly while the ball drops through it. Now our timer is ready, the ball's in position, and now we'll put our rack in place. And this bottom wire is lined up so that when the ball hits it, it will have traveled exactly 3 meters. We're going to time the last 15 centimeters of drop, and the time will be read on this meter. Now we're ready to go. Let it drop. That reads 19.8, almost 20 milliseconds. It took the ball 20 thousandths of a second to drop through that last 15 centimeters. Now we can calculate our velocity. We'll write the time. 2.0 times 10 to the minus 2 seconds. Our distance was 15 centimeters, or 15 times 10 to the minus 2 meters. The velocity then is equal to 15 over 2, or 7.5 meters per second. Now we have to square this, and I'll just do that here. So we have 56, and I'll put into this place. Now, 1/2 mv squared is 560 over 2, which is 280 joules. 280 joules of kinetic energy. Now you can see that within the accuracy of this experiment, these are about equal, and so we can say that the work is a very good measure of the kinetic energy transferred to the ball, and we can write Fs is equal to 1/2 mv squared. This is the work done. This is the energy transferred to the ball. This energy was transferred to the ball from the system we had originally of the Earth and the ball attracting each other. Now this means that that system had energy, and that the amount that it lost was equal to this. This kind of energy is not energy of motion. It's energy that depends only on the separation between the two attracting bodies. This kind of energy we call potential energy, and we measure it, too, in terms of work. The energy was put into the system from the energy of muscles. Exactly the same force was used for the same distance to put the energy into the system. Whenever we have a system of interacting masses in which the force depends only on separation between the masses, then we know that we can add energy to the system by doing work here, and know that when we release the system and allow it to do work, the energy can be returned to the masses in the form of kinetic energy. Now don't think that this is true only for gravitational attraction. There are many kinds of forces that depend on distance only. Here is one. A spring exerts a force that is proportional to distance. That's why, of course, a spring balance can be calibrated with even markings like this. A rubber band has a force-distance relationship that is interesting. It's not linear, as you'll find if you try it, but within certain limits, you can put into it energy and get the same amount of energy back. It's not always true that the force is greater with distance. In this case, for example, the magnet I have in this hand doesn't have much effect out here on the other one, but when the distance becomes small, the force becomes very great indeed. And the forces of attraction are just as great as the forces of repulsion at small distances with these magnets. It's hard to get them together without making a clatter. Now, magnets and springs both give us force-distance patterns that are reproducible. They're always the same, so we can store energy in systems like these. We're going to do an experiment using a machine that gives us a force-distance pattern that's different from any of these. Here is our machine. We've arranged to have a force that varies with distance in a rather irregular way. The force exerted on this tape is produced by a spring and cam system. The tape is wrapped around the rim of a wheel, so that when I take up the tape steadily here, the wheel turns at a constant speed. One end of the spring is secured to the table, the other to a chain bolted to the rim of the wheel. As the wheel rotates, the spring starts to stretch. Here, at the bottom of the turn, a steadily increasing pull on the tape is required to stretch the spring. As the bolt rises on the opposite side, the pull required is much less. Halfway up, the chain begins to bend around the hub of the wheel, once more stretching the spring, but this time at a much slower rate. Let's watch the machine do the work in the opposite direction. At first, the spring pulls gently. Here, as the bolt starts into the bottom of the turn, the spring begins to pull very hard. Then, as the spring returns to its normal length, the pull drops off to nothing. This is our force, and this is the device we use to measure it. This little ring is very much like a stiff spring balance. It works electronically, gives a signal to this machinery that you hear working in the background, which drives a pen that you'll see in a moment. What we're going to do with this apparatus is to do work on this system, to put energy into it, store that energy, and then let the system do work on a moving mass. This is the mass that we're going to accelerate. Now, when we transfer energy, we do work, and we have to calculate that work. And you remember that to calculate work, we have to know force and distance. And I'll show you how we're going to plot our force-distance curve. This ring has been calibrated in newtons. And when I put a strain here, you can see that this pen will register the amount. I'll put 20 newtons of force here, and you can see that the pen reads 20, 40, it reads 40, 60, and so forth, as accurately as the circuit can make the pen follow. Now I'm going to hook this ring on one side to our tape. The other side of the ring I'll hook to this frame, which can be pulled along to give us our distance measurement. So that the pen, when it's touching the paper, will trace out a curve of force versus distance. Let's attach this now, see how it works. Now, the pen is in contact with the paper. We're all set. Let's just pull and see what kind of curve we get. Well, that is a strange-looking curve, isn't it? The force, you see, goes up, and then down, and then up again. Of course, these little wiggles are there, because like any spring balance, this is a little bit jiggly. It's hard to control. I'm holding this under tension, and now I'm going to release the tension slowly and let the system do work. We'll see what the curve looks like on the way back. Well, there doesn't seem to be much difference, does there? Perhaps a little bit. Suppose we just try it again and see if we can repeat our results. Now I'll pull this again. It's rather a peculiar feeling, because we're used to things that take more force as we keep on pulling. But we've deliberately built this particular machine so that it suddenly gets easier to pull, right about here. Well, we seem to have pretty much the same curve, when I'm doing the work anyway. Now let's have the system do work again. Last time it seemed to give us a little less height. Let's see how that checks. Now it's pulling on me, but not very hard. Now it's pulling harder. And about here, it's pulling very hard. The curve tells us that this is the point where the force is greatest. The curve is also marking out the limits of an area, the area that represents the work being done. Well, there's our curve, our force distance curve. It's a pretty definite thing, and it doesn't seem to matter whether we're doing work to put energy into the system or whether energy is flowing the other way, out of the system. There's a little bit of difference, actually. These two upper curves were made when I was doing the work. The two lower curves were made when the machine was doing the work. A little energy has rubbed off here. We have to expect that in any mechanical system. Now I'm going to transfer energy to the system again so that I can store it there, and the system will be in a position to do work on the cart. Now that the energy is transferred to the system, I'm going to lock this here so that I can store the energy. The system now has potential energy, and I'm going to take the strain off the gauge. This plate is fastened over a pin so that I can hold it in place. Now our system is locked at this point, and I can release the frame. And as I do this, see the pin goes back to 0. Now I can take this ring away because we're through with it. And I can turn off the pin. Now we can pull our chart back free of the pin and think about the energy that's stored here. To find the energy, we have to know the work that transferred that energy. This work is the area under the curve. We can use a grid to find out how much work we have. These squares are 10 newtons up and a 1/20th of a meter across, so that each square represents a half a joule. Now, I've made curves with this system earlier, and I found that the number of joules of work is 25. So we have 25 joules of energy stored in the system, and we're ready to let the system do work on the cart to transfer energy. The cart has a mass of 4.3 kilograms. I'll put it here, secure it with this catch. Now we don't need this weight anymore. And now, knowing the mass, we have only to find the velocity of the cart after the work has been done on it. This is our device that we used earlier to measure velocity. You remember that these wires are 15 centimeters apart, and we can measure the time that it takes the cart to go this 15 centimeters by reading this meter. Down here, we have just a braking system, nylon threads, and a rubber bumper to stop the cart when it gets to the end of its journey. Now we're ready to release the system and let it do work on the cart. You watch the meter while I pull the switch. Just a little over 45 milliseconds. Now we can calculate our kinetic energy. The mass of the cart is 4.3 kilograms, and now our velocity is 0.15 meter divided by 0.045 seconds, and we have to square this. And now we just have to do a little arithmetic. That was quite a velocity the cart had. That turns out to be 24 joules. 24 joules of kinetic energy transferred to the cart. We did work to put 25 joules of energy into the system, stored it there as potential energy. Then we let the system do work on the mass of the cart to transfer 24 joules of kinetic energy to it. That is about as good agreement as we have any right to expect. Now remember, this force varied in an irregular way with distance, but it was the same whether we were putting energy into the system or taking it out. In either case, to find the energy transfer, all we needed to do was to find the work, the area under this curve. Now I have another interesting energy transfer to show you, and this time I want you to figure out just how you'd go about calculating the energy transfer. To start the transfer, I'll release this ball. Well, you saw a number of energy transfers there, and there were some you didn't see. But it would be pretty hard to figure out each one individually and then add them up to get the total. But if you really want to know the total energy that was transferred, it's easy. To do it again, I just do this much work on the ball. It's as simple as that. We've followed energy transfers up to a point in several cases, but there's no reason to stop after just one or two transfers. we have very good reasons for believing that energy is never created or destroyed. The chain has no beginning and no end. I'd like to go back to our first experiment and show you something else. We'll drop the ball again, and this time we'll let it hit a spike in a pine log. This spike has been set so that the top of it is on a line with our 0 mark. Watch what happens when the ball hits. All right? Well, the spike was driven down to here. Work has been done. Energy has been transferred. Let's see how that transfer went. You remember that the ball had 290 joules of kinetic energy when it hit the spike. The spike exerted an upward force on the ball and decelerated it. Took energy away from it. The ball exerted a downward force on the spike and transferred energy into it, accelerated it into the wood. Now, of course, the wood exerted an upward force on the spike and stopped it. Now, the nail isn't moving. It has no kinetic energy. The ball isn't moving. And even the energy that we originally put into the system of the earth and ball attracting each other is gone. Is energy still conserved? Let's have a look. This time, we have a device inside the spike to record temperature. Any change in temperature in this region will be recorded on this meter. Watch the meter very closely while we drop the ball. All right, let's go. Well, the drop is over. The spike is not moving. The ball is not moving. But look, the temperature's gone up. Here is energy in another form. You'll be studying heat energy soon, and you'll find that in whatever form, energy goes on being conserved.
Many of you will remember having seen the mercury spectrum. An intense blue-green line, a dark blue line, and an extremely difficult to see deep violet line. And precautions to guard your eyes against the ultraviolet, which is also produced by the moons. With the help of photographic film, we can see the ultraviolet part of the spectrum as well as the visible spectrum. Let's, for a moment, concentrate our attention on the intense line way down at the left end of the photograph. This line is measured as having a wavelength of 2,537 angstroms. This means, as you know, that all of the light coming there has the same wavelength and, of course, has the same frequency. Light coming from identical mercury atoms. But you have recently learned that light behaves as photons, whose energy is proportional to the frequency. Therefore, for all of the photons coming into the spectral line that we've talked about, they will all have the same energy, and that energy can be calculated from the simple formula that E is equal to 1, 2, 3, 9, 7. Too bad it's not 1, 2, 3, 4, 5. Divided by the wavelength of the photon, where if the wavelength is in angstroms, the energy is in electron volts. Thus, mercury atoms, which are contributing photons into the line of the mercury spectrum which we've been looking at, must all lose energy exactly equal to the photon energy, which is another way of saying that mercury atoms, when they emit photons, can only lose energy in certain sized packages. Detailed and very careful analysis of many such line spectra of this type, added to the information that was gained from other experiments, for example, the photoelectric experiment, led physicists of the early 1900s to the conclusion that an atom can only take on certain discrete energy values. That is, the internal motion of the atom can only take on certain energy conditions, not just any energy whatever. This postulate formed one of the basic principles upon which the atomic theory of Niels Bohr was developed in 1913, and was such an important postulate that James Franck and Gustav Hertz in the following year devised an experiment to test the postulate in a very simple and direct way. It is the experiment of Franck and Hertz which we wish to perform today. The question that we wish to ask is this: if it is true that mercury atoms can only take on certain discrete energy states, then can we produce these energy states by other means which do not involve photons? For example, can we produce a collision between a mercury atom and, let's say, an electron whose energy we know very accurately, in just such a way that the mercury atom will be caused to move from one energy state up to another energy state? Can we bump the mercury atom with an electron, giving it just enough energy to cause it to jump this particular special amount of energy? Now, before we look at the actual experiment, let's take a look at a large-scale and admittedly rather crude analogy. I'd like to represent the mercury atom with this dry ice disk, which you already know about, and I would like to represent an electron with a ping-pong ball. In this model, the ratio of masses is only about 1,000 to 1, while in the real atomic situation, the mercury atom has a mass almost 500,000 times the mass of the electron. But that'll be all right, I think, for the effect that I want to show. Another thing should be said concerning the velocities of the particles. You know that both particles are going to be in motion. The mercury atom will have the thermal motion of its surroundings. And we can show that for temperatures just above room temperature, the mercury atom should have a speed of about 250 meters per second. While the electron, if it's perhaps a 1 electron volt electron, will have a speed nearly 1,000,000 meters per second. And so from its point of view, the mercury atom is essentially standing still. Now let's watch this collision. As I send in a 1 electron volt electron against a mercury atom, I see that the electron comes away with almost the energy that it had when it went into the collision. I know this is true because the mercury atom does not seem to acquire any appreciable amount of energy. And of course, this is what we expect for elastic collisions with this mass ratio. But this is really not a very good model yet, because you know that with elastic collisions, you cannot transfer energy into the internal motion of the atom. So let's change the model by adding this, and this still isn't exactly the way I picture an atom, but it's a somewhat better model than the last one. We then will send in another 1 electron volt electron, and this time we see that we can transfer some energy to the internal motion. Let's try it again. And this time, watch the electron. It goes in with high speed and comes out very slowly. It has indeed transferred almost all of its energy to the internal motion of the atom. But there still is one thing wrong. If an atom behaved like this, then we would expect that we could transfer any amount of energy to the atom. For example, if I send in a slow electron, I transfer only a small amount of energy to the internal motion. If I send in a high-speed electron, I transfer a large amount of energy to the internal motion. And we have just postulated that atoms do not behave this way, but rather that there are only certain sized packages of energy which can be transferred into the internal motion. We therefore expect that slow electrons will be involved in only elastic collisions and will therefore not change their energy. But that if we speed an electron up to a proper value, that we then will make an inelastic collision and deliver all of that energy to the internal motion of the atom. Now, to make a model which would exhibit this would really be pretty difficult. So let's just go back and take a look at our original setup. We are going to use a special vacuum tube for this experiment. Which has, as you see, a rather complicated electrode structure and a big blob of mercury inside. To study this electrode structure in detail, I have another tube which I've disassembled, and we will take a good close look at this. You see in the middle a little cylindrical cathode which has a heater inside, and then there is a control grid, just a spiral of wire, very, very fine in diameter. And on the outside of this structure fits an accelerating grid, a cylindrical wire screen. And concentric with this accelerating grid is a metal anode. Now I'll show you the function of these parts in a schematic drawing. I'll start with the cathode and a heater, which will operate on a 6-volt storage battery and boil electrons out of the cathode. The control grid then will determine the amount of current which passes through the control grid and into the region between control grid and accelerating grid. I can adjust the amount of acceleration given to the electrons by means of a variable voltage, and I will measure the voltage which is used for the acceleration to give the electrons energy as they come across the gap. I will then require that those electrons passing through grid 2 have an energy of at least 1 electron volt in order that they be counted in a current meter which is attached to the anode. Now let us go back and look at the tube. We will measure the tube current as we change the accelerating voltage. And I will read the accelerating voltage on this meter from 0 to 30 volts and the anode current on the electrometer. I will use the middle scale from 0 up to 2 measured in units of 10 to the minus 5 amperes. As I increase accelerating voltage, we see first of all no current, and then with further increase the current begins to rise. If I increase the voltage continuously and smoothly, the current also rises smoothly and returns back smoothly to 0. Now we can introduce mercury atoms into the path of the electrons by placing the tube in this oven and heating it to about 160 degrees centigrade. Mercury atoms will vaporize from the mercury blob and diffuse throughout the tube using stop frame photography so that you can see the process happening more rapidly. As the mercury heats, it vaporizes from the blob, diffuses up through the tube, condenses on the cooler portions, drips down, and runs back into the blob. Now, if mercury atoms behave according to our proposed model, what do we think will happen this time as we increase the accelerating voltage? At first, of course, we will expect no current, until the electrons have acquired enough energy to get up the potential energy hill. Then, as we increase the accelerating voltage further, we will expect that the current will increase just as before. However, this time there are mercury atoms present in the space between the grids, and we will expect that electrons will be making collisions with these mercury atoms. However, as we saw in the dry ice disk experiment, those electrons will not lose any appreciable energy to the mercury atoms as long as the collisions are elastic. Therefore, even though they bounce around quite a bit, when they do go through grid 2, they will have just the same energy which they had if there were no mercury atoms present. Now, as we increase the accelerating voltage still further, we will finally arrive at a condition in which the electrons have gained enough energy in passing between the two grids so that they can deliver a full and proper-sized package of energy to the mercury atoms if they collide with such mercury atoms right here near grid 2. Then, they will lose all of their energy to those mercury atoms and will not have enough energy left to get up the potential energy hill. At this accelerating voltage, we will then expect to see a considerable drop in anode current. Let's try it and see what happens. First, I must change the scale on my current meter in order to read anode current in units of 10 to the minus 8 amperes, because with mercury atoms in the tube, the overall tube current is cut down considerably. Now then, as we increase the accelerating voltage, again, no current at first, and then the current begins to come, just as before. Electrons are being accelerated between the grids more and more. There, something's happening. A drop in current. Something suddenly happened to the electrons so that they couldn't get across to the anode and be counted. This is exactly what we were predicting. Therefore, our postulate and the line of reasoning that we used seems to be borne out by the experiment. Apparently, electrons can deliver to the atom only a certain sized package of energy. But now, you also noticed that the current was beginning to increase as I stopped increasing accelerating voltage. Let's continue with this and see what happens as I continue to increase accelerating voltage. 12 volts, another drop. Once more, an increase. Another drop, a big one. Further increase, smoothly increasing accelerating voltage. Another drop, fourth one. A fifth one. And now I'm up to the full voltage which I can apply across these grids. Well, now this really looks interesting. I think we'd better go back and do it again and see what we can make out of this result. This time, I would like to use an automatic recording device which will plot the anode current as a function of accelerating voltage. This will make a permanent record, and then we can read off from the graph the energy values at which the current dips occur. I will increase the accelerating voltage, and you remember that initially we have no current flow, so you can get an idea of the noise of the system here at the beginning. As I further increase accelerating voltage, the current begins to rise. There now starts the first dip. Once more, the current begins to rise. Another decrease, a big one this time. And then another increase. You'll notice that each inch of the horizontal scale represents 5 volts. The peaks seem to be just about 5 volts apart. Let's see if this continues. We're approaching the 5th rise. There's another dip. And now we're up to the 30 volts, which is the maximum that I want to put between the grids. Now, let's measure the voltage distance between these peaks. I don't really want to use the first peak because I don't know where the current starts to rise from zero, and also there are some extra voltages around in the circuit that aren't being measured by this voltmeter. But the distance between the first and second peak is 4.5 volts. Between the second and third peak is about 4.8 volts. Between the third and the fourth peaks is about 4.9 volts. And between the fourth and fifth peaks, about 5.1 volts. These average out to be somewhere in the neighborhood of 4.9 volts. All of them, as you see, spaced rather uniformly. Now, what does this tell us? Why should they all be just 4.9 volts apart? There are two possible explanations for this, and really this experiment alone cannot choose between them. The first answer might be that a mercury atom can absorb only packages of energy which have a multiple value of 4.9. For example, 4.9 volts, 9.8 volts, 14.7 volts, etc. Or the other explanation could be that the electrons themselves collide with mercury atoms so frequently when they get up to around 5 electron volts that they are not able to rise above that value, but rather deliver their 5 electron volts to the mercury atom and then have to start over again several times between the grids. Let me show you on our schematic why the second choice seems very plausible. First, I'll put a piece of glass over the schematic. You remember that we said that when electrons are able to accelerate and achieve an energy of 5 electron volts by the time they reach grid 2, that they then can make inelastic collisions with mercury atoms in the vicinity of grid 2, deliver their 5 electron volts to the mercury atom, and then not have enough energy left to get up the potential hill and be counted in the current meter. Therefore, a current dip is observed. If now I increase the accelerating voltage further, the distance which an electron must travel in order to acquire the 5 electron volts becomes smaller and smaller, until finally, when the accelerating voltage is 10 volts, the first inelastic collisions can occur here, and the electrons can still gain 5 electron volts of energy before reaching grid 2, can make second inelastic collisions in this vicinity, and then again are not able to get up the potential hill and be counted. Therefore, a second dip results. With further increases in accelerating voltage, you observe, of course, that the position of the first inelastic collision is here, and a second inelastic collision can occur here, a third inelastic collision here, and once more, the electrons are not counted in the current meter, resulting in a third dip. Thus, with this experiment, we can say only that the smallest of the packages of energy which a mercury atom can accept is of size 4.9 electron volts. Now, does this bear any relationship to the size of the energy package which can be carried off by a photon? Well, using our relationship between the energy of a photon and the wavelength of the light, and putting in 2,537 angstroms for the spectral line which we looked at earlier, we find that the energy of the photon is 124 divided by 254 it is 4.9 electron volts, exactly the same sized energy package. An atom, therefore, seems to absorb energy of this amount by electron collision and loses the same amount back again by photon emission. As with any good theory, a number of possible new experiments suggest themselves. For example, can we actually see 4.9 electron volt photons coming out of this apparatus when we perform the experiment that we've just done? Is it possible to deliver this energy package of 4.9 electron volts to the mercury atom through collisions with particles other than electrons, for example, with photons? And indeed, because there are other spectral lines present in the mercury spectrum, do we not expect that the mercury atom can absorb other-sized packages of energy than this single 4.9 electron volts? And then, most important of all, is this a particular behavior of mercury atoms, or do all atoms do this, and we should test this? Now, of course, to do these experiments requires equipment somewhat different from this. However, these experiments have all been done, and your text gives you references to some of this work.
The demonstration and interpretation of the inelastic impact of 4.9 volt electrons with mercury atoms in the film has been so clear that no supplement by myself is necessary to this experiment. However, I may speak a moment about another experiment we made to study what the results of these inelastic impacts. You know, and it was mentioned before in the film, that one would expect that if 4.9 volt electrons lose all the energy to excite light, that the line 2537 would occur because the quantum of this ultraviolet light has exactly the same energy than the kinetic energy of the 4.9 volt electrons. So we made an experiment with a simpler apparatus. I have a reprint of that with me here, of that old paper. It was difficult to find because it's in the library, always somewhere nearly 50 years ago, somewhere in the attic. We can see the apparatus consisting only of two electrodes, a glowing wire, and another electrode, the anode, included in a quartz tube, because ultraviolet light should come out and would not penetrate through glass. This quartz tube contained mercury, and we heated it to a suitable pressure so that enough inelastic impact would occur. And we put a potential difference between the two electrodes a little bit higher than the 4.9 volt. If we put that before the spectrograph, which we bought for that purpose, then we see that indeed only one spectral line occurs, and we have also in this picture one normal spectrum taken with the same bulb using higher voltages so that electric discharge occurred. You will see in the spectrum also a continuous spectrum in the visible region, which is stray light coming from the glowing wire. But that's all one can see. The spectrum gives only the line 2537, and no other spectral line occurs. And so we had really the result which one might expect. Indeed, we had a result which was in best agreement with Bohr's theory, which said that atoms, or better the electronic system of atoms, can exist only in different discrete states of energy, and that light emission occurs if an atom was excited to a higher so-called quantum state and reverts by light emission to the ground state. The line 2537 is the transition between the first excited state and the ground state. It might interest you that when we made the experiment that we did not know Bohr's theory. We have neither read it nor heard about it. We have not read it because we were negligent to read the literature well enough. And you know how that happens. And if, on the other hand, one would think that other people would have told us about it. For instance, we had a colloquium at that time in Berlin in which all the important papers were discussed. Nobody discussed Bohr's theory. Why not? The reason is that about 50 years ago, one was so convinced that nobody could, with that state of knowledge we had available at that time, understand spectral line emission, that if somebody published a paper about it, one assumed probably it is not right. So we did not know it. That we made the experiment and got the result which confirmed Bohr's theory was because we hoped that if we find out where the borderline between elastic and inelastic impact lies, where the minimum velocity of electrons to emit some light lying, only one line might appear. But we did not know whether that would be so, and we did not know whether at all an emission of an atom is of such a type that one line alone can be emitted and all the energy can be used for that one purpose. The experiment gave it to us, and we were surprised about it. But we are not surprised after we read Bohr's paper later, after our publication, and when we made these other kinds of experiments, and many other people made experiments of that type, which are all in best agreement with this basic concept of Bohr's theory. Indeed, this experiment is a good proof, all the experiments on inelastic impact of the theory, and you know that this first paper of Bohr is really the fundament of the whole development of modern physics, the whole development of attempts to understand the structure of atoms and molecules and even of the nuclei in detail.